let's start the second half of class here. Let's look at Bayes' rule. It's a general formula illustrating the problem we did at the end of the lecture A here. The situation is you know certain conditional probabilities, but you don't know another one that you want to know. We would like to know the conditional probability of A given B. We happen to know we're given the probability of B given A, and also B given A complement. Those are the things that we know. In the problem that we did here on the board, if you want to, you can see both of these here. A was the disease A, having the disease A, and B was when the test came back positive. So this first step in deriving Bayes' rule says use the formula for conditional probability. Conditional probability of A given B has occurred is the unconditional probability of A and B occurring divided by the unconditional probability, the regular probability that B occurs. That's just the formula for conditional probability. The next step to deriving Bayes, the formula here, is to break the probability of B occurring into two pieces based on the addition rule for disjoint events. Look at the bottom here. The probability of B occurring can be thought of as the sum of these two things. Why? Draw a picture to help you understand it. Here's A, here's B. Thinking of the probabilities of these events as representing the areas, which you can do if you want. The probability of B occurring is the area of the entire circle for B. But that entire circle for B can be broken into two pieces. This piece right here and this piece right here. This piece is A and B. That's the probability of A and B. I switched them around there, it doesn't matter. That's this piece. This piece out here, the crescent shape, is the probability of B and not A, the complement of A. Everything inside this crescent shape is inside B, but not inside A. So those are disjoint, non-overlapping events, no intersection, empty intersection. Therefore, by the addition rule for disjoint events, the probability of B occurring is the sum of these two. Then both of those are involving the word and because of that, you can use the general multiplication rule for both of those. And you want to use it in the form that you see here and here because we are assuming we know these two probabilities, as well as every other probability that you see in here. So again, for the problem that was at hand, this number was the 0.0001, 1/10,000th. This one was the number 0.99. This one was 0.9999, people who do not have disease A. And this one was the 0.98. And the top, this was 0.0001, and this one was 0.99. B is when the test comes back positive in the picture. Okay? So you definitely can derive Bayes' formula for from more basic rules. This formula is hard to remember. And I don't, as far as homework goes, when you will have a homework problem where you have to use this, I'd prefer you think about it with a tree diagram, like I did here. That's a better way to think it through, I think, than just using a formula. But if I gave you that formula for the test, you should be flexible enough to use it if you needed to. Okay? So it, again, is good to think about it both ways. All right, on to binomial distributions, which we introduced last time. We're thinking about it in the context of Rod Carew's hitting. If you've never heard of Rod Carew before, he was the Minnesota Twins and also Angels player from the past. And in the past, he was Los Angeles or California or Anaheim Angels. I forget what it is now. What is it? Anaheim, California? What is it? Los Angeles. They've labeled the Angels California, Los Angeles, and Anaheim at various points in time. It's kind of crazy. But anyway, Carew played for the Twins and then the Angels, and he was a very good hitter. Played from like around 1969, I think, until 1983 or 84, that's my guess. Anyway, 1977 was his best year. He was the MVP that year, and his batting average was .388, meaning he got a hit in about 38.8% of his official at-bats, and you can interpret that as a probability. We're pretending we've traveled back to 1977 and we're asked to assess the chances in the next game. If he gets up 5 times, what are his chances of getting 3 hits? We did this last time. I'm going to go through it again today. Emphasizing the rules, you should be able to think this through. Not just use formulas, but also think through the ideas to use simpler formulas instead of the more complicated formula we're going to come to. First, it would be good to list out the possibilities of successes and failures, hits versus non-hits, that could occur, though you do have to be careful because unlike coin flipping, where heads and tails are equally likely, success and failure is not equally likely. Okay, and so you don't want to just look at the sample space. You also have to think about the probabilities of each possibility within that. Here is the list of 32 possibilities for S's and F's based on 5 at-bats. The event of getting exactly 3 hits, there are 10 outcomes that give you exactly 3 hits. But again, warning, the answer is not 10 out of 32, which we reduced to 5/16. That's not the answer. Because failure is more likely than success, the answer is going to be smaller than 10 out of 32. How small? We have to figure that out. In answering this question, you do need to use both the multiplication rule for independent events and the addition rule for disjoint events. They are both relevant for figuring out the probability. Again, I'm going to go through it quickly. Keep your mind on. Try to think it through with me here. It's independence to the rescue initially, at least. If we assume somewhat reasonably, again, it's not a perfect assumption because there are different pitchers he can try to hit against. There are different game situations. There's different stress levels during a game that could affect his probability of getting a hit on any at-bat. Although Rod Carew was so good, he was pretty much good against every pitcher out there, that maybe it's more reasonable for him to assume independence. So, for example, we can assess the probability of this particular run of successes and failures, SFSFS. First at bat he gets a hit, second he doesn't, third he does, fourth he doesn't, fifth he does. If we assume the independence of those events, this is the multiplication rule for independent events applied to 5 events, and you can apply it to 5 events. Find this probability by finding the probabilities of each of these things and multiplying them up. And they are all regular probabilities, not conditional probabilities. Because P of S occurs 3 times and it's always the same number, 3.388, we can really say that's P of S to the 3rd power. P of F occurs twice, so we can say that's P of F to the 2nd power. P of S, the probability of success is 0.388. P of F, the probability of failure, is 1 minus 0.388, which is 0.612. And the probability of this particular outcome, success, failure, success, failure, success, in any game with 5 at-bats is about 2%. However, there are 10 ways you could get 3 hits in 5 at-bats. Therefore, you really have to use the addition rule to find the total probability of getting 3 hits in 5 at-bats. Because each of those ways you could get 3 hits in 5 at-bats are disjoint outcomes. If you got SFSFS, it's disjoint from getting SSSFF. Okay, if that occurs in a game, that won't. For Rod Carew, if that occurs, then that won't. Those are disjoint outcomes. They're really events with one outcome, disjoint events. And there were again 10 ways 3 S's and 2 F's could occur. So you really have to add this to itself 10 times, which is the same as the effect of multiplying it by 10. Multiply this by 10, you're going to get this. He's got about a 22% chance in 1977 of getting 3 hits and 5 at-bats in any game where he got 5 at-bats. I did share with you that spreadsheet that's got his game logs in it. I once again don't have the time to look at that with you. I wanted to, but I think we're going to be short on time. I do want to get back to simulation. I was hoping to last time and then today, but we just have too much other stuff to do. I think for sure next time, next Tuesday, we will get back into simulating these things and we'll be looking at the spreadsheet. I did ultimately make a graph of his probability distribution in this setting. Lots of slides in between. We're going to come back to those other slides. On the spreadsheet, I made these graphs. This graph you would call a probability distribution. In this case, for the number of hits in 5 at-bats for Rod Carew in 1977. There's 3 hits in 5 at-bats. What's the probability? We got about 22%. The height of that rectangle is about 0.22. I did it for 0 hits, 1 hit, 2 hits, 3 hits, 4 hits, 5 hits. Those are all the 6 possibilities that could happen with 5 at-bats. His chance of going 0 for 5 was about 9%, it looks like. His chance of going 1 for 5 was about 0.27 perhaps. His chance of going 2 for 5 is the highest, about 0.34 or so. This was 0.22. This one looks like it's about 0.7. And only about a 1% chance of going 5 for 5. Only about 1 out of every 100 games where he had 5 at-bats will he go 5 for 5, even though he was such a good hitter. Okay? That's nice. I also made a related graph that's called the cumulative distribution for the number of hits in 5 at-bats. You want to think of this mostly as being points, though I did connect the dots. The heights of these points represent the probability of getting the given number of hits or fewer. So for example, the probability that x is less than or equal to 3 is the height of the graph above 3, which is about, I don't know, 0.9 or so. You could find that by adding up these probabilities, because those are disjoint events. Getting 0 hits, 1 hit, 2 hits, or 3 hits are disjoint events. So you can find the probability of getting less than or equal to 3 hits by adding up those probabilities by the addition rule for disjoint events. If you add up these first 1, 2, 3, 4 numbers, you should get close to whatever the height is there, about 0.9 or so. Maybe a little bit bigger than 0.9. Okay, that's what this graph is showing. The lines connecting the dots are just there for visual effect, okay, to see the upward trend. You really want to focus on the individual points that the lines connect to. These graphs have some relation to calculus if you've taken calculus. Some relationship to derivatives and integrals, but I'm not going to get into that because most of you probably have not had calculus. If you had calculus, you could think a little bit about what I might mean by that. All right, so how do you calculate these binomial probabilities? Here's the key formula right here. To find the probability that x equals a particular number k, k represents an arbitrary possible value for x, you calculate, first of all, this thing called the binomial coefficient. N choose k is the way to read that. It's related to combinations, the idea of a combination that you probably learned about in the past. Sometimes often written NCK. In fact, on most calculators, it comes out that way. I want to compute this. And the formula for it involves factorials. N factorial divided by k factorial times n minus k factorial. Where, for example, 5 factorial means 5 times 4 times 3 times 2 times 1. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, etc. The only exception to that pattern is 0 factorial, which by definition is 1, not 0. It's a definition. I guess these are definitions as well. Why should 0 factorial equal 1? It's to make the formulas work out. That's why. Okay? So that this formula works out even if k, for example, is 0. The formula still works, right? If you define 0 factorial to be 1. Okay, that's the only reason. Makes the formula work out nice. P to the k means your probability of success to the kth power number of successes. P for Rod Carew is 0.388. And k for the problem we were thinking about was 3. Going 3 for 5, 3 successes. 1 minus p, which is also sometimes called q, by the way, in this setting, is the probability of failure. 1 minus 0.388 was 0.612. n minus k is the number of failures. If k is 3 and n is 5, 5 minus 3 is 2. He had 3 successes and 2 failures when he gets 3 hits in 5 at-bats. So let's go ahead and use this now for Rod Carew's example here to find the probability of getting 3 hits to confirm the answer we got already. The formula says in 5 at-bats, do 5 choose 3. I do want you to be comfortable with writing it that way. You could also write it this way. You should be comfortable either way. Times 0.388 to the third power. K is 3. P is 0.388. Times 1 minus 0.388, which was the 0.612, to the 5 minus 3 power, which of course is 2. I showed you this calculation already on another sheet here. This was the 10 right there. Can we confirm this is 10 with the factorial formula? Yep. We can confirm this is 10 using the factorial formula. It's 5 factorial divided by 3 factorial times 5 minus 3 factorial. 5 factorial divided by 3 factorial times 2 factorial. 5 factorial turns out to be 120. 3 factorial is 3 times 2 times 1 is 6. 2 factorial is 2 times 1 is 2. That's 120 divided by 12, which is 10. It does work out. When n and k are big numbers, especially when n is real big and k is like halfway between n and k, between 0 and n, these factorials can be quite complicated to compute, you might say, although I would call it fun. Where is it? Ah, I missed it. Where's my fun slide? Binomial coefficients can be fun. Calculate the following binomial coefficients. That, and that. Ugh. Let's do one of them by hand, and then we'll check the other ones with the calculator. Actually, these can be fun. I'm serious. These can be fun to calculate, sort of by hand with some calculator help. 20 choose 9 is 20 factorial divided by 9 factorial times 29 minus 9 factorial, which is 11 factorial. This is great. This is great fun here. Watch. 20 factorial is 20 times 19 times 18 times 17. What? Am I calling this fun? Sure, why not? Why not stop at 11 factorial? Because I'm going to cancel with the 11 factorial on the bottom. I could continue writing 11 times 10 times 9 times 8 times 7, etc. To save time, I'm not, because I don't have to, because it'll cancel with the 11 factorial on the bottom. Write out the 9 factorial completely. Write the 11 factorial. It cancels with that 11 factorial. And then the rest cancels in a lot of fun. For example, you can cancel the 20 with, for example, the 5 to leave a 4. You can cancel the 18 with the 6 to leave a 3. Everything in the bottom is going to completely cancel. Not everything in the top is going to completely cancel. The 16 there can be canceled with the 4 there to leave a 4. 15 here can be canceled, hopefully with something. Yeah, the 3 to leave a 5. 14 can be canceled with the 7 to leave a 2. The prime numbers can't be canceled with anything on the bottom. 12 can be canceled with, for example, the 2 to leave a 6. We can do more canceling. We can cancel the 9 here by doing what? Canceling with this 3 and partially with this 6 to leave a 2. Maybe I should have canceled the 18 with the 9. And what else? We didn't have the 8 left to cancel. The 8 can cancel with this 4 and this 2, for example. What's left? What's left is 19 times 17 times 4 times 5 times 13 times 2. Now use your calculator. Hopefully I didn't make a mistake. Anybody see if I made a mistake anywhere? Look okay? Maybe you've done this before. I do think it's kind of fun. All that canceling is kind of fun. You get out your anger without canceling. Right? When a mathematician is angry, they start canceling stuff. 19 times 17 times 4 times 5 times 13 times 2. It looks like the answer is 167,960. If I did not make a mistake. 167,960. Let's check that with the calculator. Graphing calculator can be checked if you type in 20 and then look for your choose function, which if I recall correctly on my calculator is under math mode, PRV, which stands for probability. And then I see NCR there for the third option. That's like NCK. I was in my math mode, probability PRB. I press the NCR. Then I press 9 for 20, choose 9. And yeah, I got the same answer, 167,960. Choose 10 is bigger. I'm not going to bother calculating that one. 20 choose 11 turns out to be the exact same answer because of the symmetry in the factorial formula. 20 choose 11, you'd have an 11 factorial there, and a 20 minus 11, or 9 factorial there. The symmetry in the formula would give you the exact same answer. Let's confirm that with the calculator. 20, math, PRB, NCR, 11, not 111, is the same answer, 167,960. Okay? I had a little fun with this with Mathematica too. You don't have to do the Mathematica, but I had fun making an interactive version of Pascal's triangle to see these numbers. Here we go, you ready? Can you see this? The numbers are in Pascal's triangle. Maybe you knew that, maybe you didn't. What's Pascal's triangle again? It's a triangle that you can make where each number, for example, this 5 is the sum of the two numbers above it that are just to the left and just to the right. I couldn't get these out to align real well. This 56 is supposed to be the sum of these two numbers, 35 and 21. And I made it interactive. I made it so that just with a little bit of code here, just this much code, I can make this triangle bigger or smaller. And I made it big enough to include a 21st row, which is the numbers you get from 20 choose various things. And there you see right here the 167,960 here and here. And evidently this number, 184,756, evidently that's 20 choose 10. And you can check that with your calculator. Okay, so for me that's fun, making some Mathematica code to make this interactive Pascal's triangle that I can use, and I can make it even bigger if I want to. I can just change this number and make it really, really big. Of course, you lose all the formatting if you make it too big because it doesn't fit on the screen. But I think that is fun. Anyway, that's my Mathematica simulation for the day. Where are we? 7 minutes left. So that's the essence of binomial random variables. You can also do binomial random variables on a spreadsheet. They also apply to binomial settings, which you read about. You've got a fixed number of trials, a certain probability of success, you're after a certain number of successes, and you're assuming independence. I'll let you read about that again. Here's how you do it on a spreadsheet. I'll summarize this in more depth next time. That's the way you can calculate binomial probabilities. Binomial distributions also have a couple special properties for the mean and standard deviation. That's in the book, these formulas. I want you to spend time thinking about why the first one makes sense. The second one's harder to make sense of. But the first one definitely makes intuitive sense. if you think about it correctly. I'm not taking the time to think about it correctly here. I don't want to take the time for that because I want to get to one more topic, the Poisson random variables. We will come back to this next time. But make sure you read about these formulas and you think about why the first one makes sense. It does make good intuitive sense. You can predict the first one without even doing any derivations. Second one's more complicated. All right, let's go on to Poissons. A Poisson setting is when you're also trying to count a certain number of things that could occur. Just like with binomial, we were counting the number of successes and a certain number of trials. The key distinction between a Poisson setting and a binomial setting is that you don't have a fixed number of trials. You're counting how many times something happens, like the number of earthquakes in Southern California in the next year, for example. And you don't have a preconceived notion of how many earthquakes there could be. It's not a fixed number of trials. But you do have a past data that tells you the mean number of earthquakes every year, above, say, magnitude 4.0, that occur in Southern California. You've got past data, and you're trying to model that past data to predict future results. This would be important for insurance companies. They'd want to know about what to expect with earthquakes in Southern California. Mu is going to be the mean number of earthquakes per year in Southern California. You have to define what Southern California is, below some place in the map of California. And you'd have to define what's your earthquake size that you're looking at. I said 4.0 per year, or 4.0 for the magnitude of the earthquake. That's the formula for calculating the probability that x equals a certain number of successes. In this case, success is bad. It's an earthquake, or a number of earthquakes. Kind of a crazy looking formula, a little strange. Does it still involve factorials, like the k factorial there on the bottom? E to the negative mu power, where again mu is the mean count from the past, times mu to the k power divided by k factorial, where e is this strange looking number, 2.718281828,459, blah, blah, blah. E, you may or may not know, is actually a very special number in math. It's just as special as pi is, believe it or not. It is irrational, just like pi. Its decimal expansion goes on forever without a repeating pattern, or without any pattern so far as people can tell. People do memorize pi's digits, but I don't know many people who memorize e's digits. There should be competitions for that, I think. That's how you find probabilities. Let's do a basic example. I looked it up online. I saw at a certain spot online that typically, in a typical year, Southern California experiences in the ballpark of 15 to 20 earthquakes of a certain magnitude or higher per year. I don't remember if the magnitude was 4.0 or higher. It's the size of the earthquake. It might have been 3.0 or higher. Let's go ahead and assume U is 15. Let's pretend Southern California has 15 earthquakes on average per year, based on past data, above a certain magnitude. The magnitude could be 4.0 or higher, or maybe 3.0 or higher, the size of the earthquake. This formula would say the probability that there are, for example, a smaller number of earthquakes, like 10 per year, could be calculated with this formula. The formula would say, take this number e, raise it to the negative mu power, the negative 15th power, which is going to be a very small number. But then the next number is going to be pretty big. Then multiply that times 15 to the 10th power. Mu is 15, k is 10 here. Divide by k factorial, that's 10 factorial, that's a big number. You got a combination of small and big numbers. It's hard to tell how big this final answer is going to be just by looking at it. You've got to use your calculator to calculate it. Most scientific calculators should have an E. For me, it's above my division symbol. I can do my second function and press the division symbol, and there's the number E. Up to the calculator's accuracy, it looks like it's going to be a repeating decimal, but that's an illusion. It's not. It doesn't keep going 1828. That's an illusion. If I raise that to the negative 15th power, I do get a very tiny number. About 3.06 times 10 to the negative 7. Very small. But then I'm going to multiply that by 15 to the 10th power. 15 to the 10th power is a very large number. Perhaps this product will be still pretty large because 10th power is bigger than 10 to the negative 7th power. Yeah, that's a pretty big number. But now I need to divide by 10 factorial. And to get a factorial, I think I need to go back to the math mode and probability again, on my calculator at least. I need to get an exclamation point in there. I go to my math mode. Oops, wrong mode. Math. Then I go over to PRV again. And then the fourth one down is an exclamation point. There we go, 10 factorial. The final answer is going to be between 0 and 1, and it is about 0.0486, about close to a 5% chance that if Southern California averages 15 earthquakes per year, that they're going to have actually 10 in a given year. Okay? Give me one more minute, maybe 30 seconds here. You can do this with a spreadsheet as well. I've got it on the slides here. You can look at this and try it. You should try it with a spreadsheet. There is information about something called a Poisson setting that you should read about. It's more technical than a binomial setting, but you should read about it and think about it a bit. And I made graphs for two different Poisson distributions, one based on assuming the mean is 15 and one based on assuming the mean is 20. They both look fairly symmetric, like normal curves, but one is shifted over to the right more. If the mean mu is small, like 1 or 2 or 3, you do end up with skewed distributions, not symmetric ones. Okay? All right, see you next time.